Today I'm going to be talking about the formation of the solar system, and we're going to start from the formation of the Milky Way galaxy. Now, based on a new model of the evolution of the universe, in which the first galaxy formed around 126 billion years ago, we can look at the position of the Milky Way galaxy, and the galaxy is located around 26 million light years from the center of the universe. And based on the evolutionary model, the number of galaxies in each to form every 14 billion years increases by a factor of 20. So the first galaxy formed, then 14 billion years later, there were 20 galaxies. A further 14 billion years later, that has increased to 400. And we can look at the region between the Milky Way galaxy and the center of the universe, and we conclude that we are at the outer part of the 400 galaxies closest to the center of the universe. So that means that the Milky Way galaxy must have formed around 28 billion years after the first galaxy. So that puts the formation of the Milky Way galaxy an estimated 100 billion years ago. Now, the Milky Way galaxy didn't form in its present form at that time. What formed then were spherical regions of gas and dust. And what we can model is that if two spherical regions of gas and dust form in their vicinity of each other, what happens is that the tidal forces create the spiral arms, and we get from that a spiral galaxy with two spiral arms. Now, the structure of the Milky Way galaxy suggests that it results from not just a simple structure of two spiral arms, but a merger of two spiral galaxies. Now, this process of galaxy merger takes typically 20 to 30 billion years. So for a merger of a merger, we're talking around 40 to 60 billion years. And when the spiral galaxy forms in the first instance, it creates star forming regions. And in the process of evolution, once stars have formed, we get the heavier elements from a supernova explosion. Now, an important factor to take into account when considering the evolution of galaxies and star systems is angular momentum, because angular momentum is conserved, and it's conserved over a merger, and it's conserved over a supernova explosion. So we can say that any rotating object in the universe acquired its angular momentum from the merger of two galaxies. And this applies to the reason why spiral galaxies are rotating, the reason why the central black holes are rotating, often at quite high speed, and the rotation of the solar system. The angular momentum for that actually comes down to an effect from the merger of galaxies. And when you look down at the level of a star, you can see that when a star forms from a diffuse cloud of elements, gas, dust, a small component of angular momentum will result in a single star, but a large component of angular momentum must result in a binary system, because that's the only way in which that larger quantity of angular momentum can be accommodated. And we find that about a third of the star systems in the Milky Way galaxy are either binary or multiple star systems. And it's not obvious when you look into the night sky, because these binaries appear, they're close together, they appear as a single star to the naked eye. Now, the solar system can be thought of as something that nearly formed as a binary system, with the Sun and Jupiter as the potential points of the potential stars within the system. But Jupiter is much, much smaller than the Sun. And in fact, there wasn't enough angular momentum for a binary system to form for the solar system, but there was too much angular momentum for a single stable star to form. And so our hypothesis is that the solar system formed initially as a single fast rotating star, which was unstable. If we look at the way stars form, they form from a cloud of gas and dust and heavy elements. And the cloud of gas and dust that formed the solar system must already have contained all of the elements of the periodic table, which are found on Earth. And that cloud, which formed from a star, was rotating because that is the observation that the solar system is rotating. So if you imagine, we've said earlier that a rotating star which goes supernova will preserve its angular momentum. So if this cloud of matter originated from a supernova, the matter would have been ejected out by the supernova explosion. But the trajectory, if we take a single point, the trajectory of the matter would be to go out into a kind of orbital path, but ultimately it will collapse back into the central region, and that will form a star. So what this says, if you imagine a particle here towards the periphery of the cloud of gas and dust, there's no way that that particle could fall in towards the center and then go into some kind of protoplanetary disk of gas and dust in orbit around the sun, because its trajectory must be back into the center. So this rules out the current idea that the planets formed from protoplanetary gas and dust in orbit. So what the hypothesis says is that the material in the cloud collapsed towards the center, and it's rotating. So if we imagine the heavier elements falling towards the center, and the lighter elements like hydrogen and helium being at the outer region of the cloud, but you can see that because of the rotation, the shape is no longer spherical. It turns into a shape where the profile is an ellipse. And if you think about what happens to an ice skater who's rotating on the ice, if they pull their arms into the center, they rotate faster. And this kind of mechanism is happening as the heavy elements fall in towards the center. The core of the system rotates faster and faster. So that speed of rotation increases. So looking at from the top, it's still circular. But because of the shape, it becomes increasingly unstable. And the hypothesis is that that lack of stability means that a body of material is ejected from the sun. And if this were just a simple body of matter, you might argue that, well, this is just going to be projected out some distance, and then it's going to fall back in towards the sun on a kind of orbital style path, but with the sun at the focus. So all the matter would fall back into the center. But that doesn't take into account the fact that this is fast rotating, and in particular, this body of material is fast rotating. So this indeed would spin off material in all directions as it goes on its trajectory out as far as the Kuiper belt, and it's releasing material all the time. And that process of rotating spins off the planets and their moons, and additional debris, which is in the form of the asteroids. But the important point is that when we say planets are thrown off in all directions, only those planets with a circular orbit will survive, because if a planet is on an elliptical orbit, it will fall back towards the sun and eventually be recaptured by the sun. So what's left in from this chaotic start, what's left is a well-ordered system of planets in an approximately circular motion. And indeed, the presence of the planets in their orbits will clear out any asteroids that happen to have been left in that vicinity. So this is why we see all the craters on the moon, because the asteroids which were in the Earth belt have fallen into the Earth and the moon. But of course, any asteroids falling on Earth will, over time, due to the nature of the Earth, most traces would be lost. Now, we talked about the heavier elements falling in towards the center. So if you can imagine this structure as being a layered structure of elements, approximately in the order of the periodic table as they collapse in. And so somewhere within this structure, we have an oxygen layer, so that when the core is rotating faster than the outer regions, the core becomes unstable and breaks through the outer layer, taking the oxygen with it into the hydrogen layer. So we've got a sudden mixing of oxygen and hydrogen as part of this process, and this then explains the abundance of water. And it's quite reasonable to suppose that from our observation, a lot of that water layer appears to have formed in the orbital region of the Earth. So not necessarily a part of the Earth in its initial formation, but gradually accreting onto the Earth, because individual molecules of water can still be in orbit out in space. So what evidence do we have for this hypothesis? Well, it's hard to see how a protoplanetary disk could form both the planets and the moons in orbit, and with the rotation that they have. The hot molten core of the Earth is material coming from the hot molten core of the Sun. And it's hard to imagine that that hot molten core would be able to be accreted by a process of just cold dust particles in a protoplanetary disk. We talked about the presence of water. The asteroid belts, well, the asteroids don't look like the accretion of gas and dust. They look like fragments of solidified liquid material from this process which we're describing. And the whole idea of accretion of tiny particles into larger particles, just because gravity on that scale is very weak, the idea that the accretion of particles could form asteroids and planets doesn't really make sense. And finally, the presence of helium on Earth. If everything accreted based on a cloud of gas and dust, well, we can see that the process of formation of the planets would have the same source material. So the Earth would have been surrounded by hydrogen and helium, but that would all have escaped the Earth's atmosphere because the gravity on Earth is not enough to hold hydrogen and helium in place. But we do find helium on Earth, and we find it in large caves in various places. And this is where the chaotic formation of the molten Earth had bubbles of hydrogen and helium, which were trapped and still here to this day. And that process couldn't have happened if it accreted from gas and dust, because the helium just would have dissipated. So that's a long history. It goes back 100 billion years. And I mentioned the wonderful picture that was taken of planet Earth from a very great distance. And it just reveals the Earth to be a pale blue dot in space. And so thinking of this very, very long history to create a habitable planet with life, we need to think about sustainability and how we ensure that this habitat, this cradle, is sustainable, not just for 10 years, not just for 100 years, but ongoing.